Imagine you are a traveler venturing through an unknown land, not guided by landmarks or maps, by the sheer feel of the terrain under your feet. The peaks of valleys tell stories not of distances, but of how one space can flow into another, bending and curving in ways that defy everyday intuition. You might walk in circles or venture out in a straight line only to find yourself back where you started. In this fascinating field, the idea of space transcends what we usually perceive. It helps us understand not just the physical world, but also abstract structures that govern everything from the form of a coffee cup to the very fabric of the universe. Today, we are fortunate to have with us someone who traveled these abstract landscapes, someone who has explored the shapes and structure that defined our understanding of mathematics. Our guest speaker, Dr. Somnath Bose, is an associate professor in the Department of Mathematics and Statistics at IISER, Kolkata. He completed his Ph.D. at the State University of New York, Stony Brook, under the mentorship of the renowned Abel Prize winning mathematician Dennis Sullivan. Dr. Basu's expertise in topology connects the mathematical theory to a wide array of disciplines. Please join me in welcoming Dr. Somnath Bose and a warm welcome to all our subscribers tuning in for today's episode. Together, we will explore the intricate world of topology. Welcome, Dr. Somnath Bose.
Yeah, thank you so much, Shaunak. It's a pleasure to be able to interact with people interested in thinking and learning about topology. And I hope it would be a learning experience for me as well. Thank you.
Absolutely. So, Dr. Somnath, to start, before we go into topology, I would like to know what was your childhood inspiration that you took up maybe mathematics and then later specialized on topology. So, what was the area of interest for you?
I would say, mostly until the 10th standard. So I studied in ICSE board, and my school was actually a school very close to my house, St. Mary's uh, Orphanage and Day School. Now I think it's called St. Mary's Day School in Dum Dum. So I liked math and also other sciences, but nothing particularly stood out. And then in the 11th and 12th, when I joined St. James, because St. Mary's did not have any uh, like 12th standard. So there, the math teacher, Professor Dept, he had at some point said there is this Olympiad and you guys can try sitting in. So some of us sat in, and I managed to do well in the regional Olympiads and somehow got selected into the national one. Went to the training camp. So there, whatever was taught, I kind of liked, and so that was kind of the starting point. And then, of course, people sort of made me aware that there are these, programs at ISI, Indian Statistical Institute, and so that was that. So I hoped to get into that, and I did. And then from there, one thing led to another, and then went to do a PhD at Stony Brook, and then there, after interactions with other mathematicians, I decided to sort of zero in on topology. So yeah,
Okay.
that's kind of in short the trajectory. Yes.
Okay. So, although I hope you won't mind, was the family, your parents, your father, anybody were, I mean to say, involved in mathematics whatsoever that you saw and developed that interest?
No, not quite. I mean, no. So nobody was in academia, even in my mother or my father's side to speak of. So my
Hmm.
father was an engineer, and my grandfather, who was good at playing chess and these kind of strategic games, I did learn a bit of chess from him. Although I don't play it now, so he was good at that. But apart from that, I mean, there was nobody directly involved in the family who could say, "Okay, read this, do that." It's just that the Olympiad thing happened, and then the training camp was an eye opener. You get to meet with like-minded people, learn sort of new methods of thinking about things. So I think that was a big turning point for me, and also for many others that I know of.
Thank you, Dr. Somnath. We already got questions. I told you that the subscribers are eagerly waiting to meet from you. I will take up the questions one by one. But before that, I would just like to know that if you can tell, I mean to say, not in very technical terms, what is topology and how it is different from geometry?
Okay, so I mean, I guess see, if you go through the origin of the word, the topology, it's a combination of two Greek words, and it basically means, topos, and which is like location, and then study. So it's basically translates to study of location, which is how it originated. So it's a branch of mathematics which studies properties of a geometric object which is preserved under continuous deformations. And one can make this precise, but by these I mean you can stretch, twist, bend, but you're not allowed to cut, do a puncture, poke a hole, so that kind of stuff. So you're studying properties of actual objects. These could be abstract objects, as you'll see in some examples when we discuss later on, but you want
Right.
them to be preserved under such deformations. And so, as a quick example, you can take a square made out of just a piece of wire, and then you can deform that just by putting pressure and deform it to a circle. But you can convince yourself that you cannot deform this square, which is made out of wire, into a figure 8 without cutting and rejoining it. So that's kind of what you are dealing with in topology. It's different briefly from geometry, because in geometry quite often these deformations are very rigid, because there is a notion of distance and measurement in the background context, that you want things to
Right.
preserve angles, preserve distances. Here we are not really concerned with those things, because those are allowed. So dilations are perfectly valid continuous deformations, but dilations do distort distances. So from a geometric standpoint, a circle and a square are not similar, but from a topological point of view, they are similar or equivalent, or as you see, there's a term called homeomorphic. You can say they're homeomorphic if you want to put it that way.
Right. Thank you for that. Pavan Gaonkar is asking, I would like to know how topology is related to physics and in what way?
Okay, so I can answer that. So this will probably involve more algebraic topology and differential geometry. So, will it be better if I sort of answer it after we discuss
Okay,
like a
sure,
bit more basic things
sure,
on
sure.
topology first? At least the
Right,
examples I know of, they involve, not point set topology, but rather the modern versions of it. So,
right, right. So in that case, Dr. Somnath, when we are talking that, for example, I'm taking a kind of a square. Now, can I imagine that I am blowing air into it and it is slowly expanding into another form? Now the square which has got the sharp edges, when I blow air into it, it becomes a kind of a football or a soccer ball, and then it slowly expands. So the the square which has got the edges now becomes a kind of a continuous thing, which where it takes the shape of a soccer ball. Now you told just now that the cutting and tearing or poking is not allowed. Is it that because if I take the square or any kind of a function, the cutting or gluing, will that make the function discontinuous? Is it that it is a rule that it is not being allowed in topology?
no, so it's not like a like involving a function. So the picture that you said can be made precise. That if you imagine how to deform a circle to a square, so then one way to do it is imagine the square being placed circumscribed inside a circle of the appropriate radius. And then if you literally imagine a light source at the center of the square, then the shadow that the square forms on the circle is the circle itself. So that directly gives you an explicit map. You can write down, it's a map in XY plane, right? Everybody can write down such maps. And then you can say that, oh, we have a map, and then you show what, in topology or otherwise, using the notion of continuity, that this is a continuous map. It's a 1-1 map, it's a on-2 map, and the inverse is also the reverse sort of light projection. You just take the shadow and go to where the
Correct.
source comes from. So that's why they are the same in topology technically, and it's an explicit map. As far as poking holes or sort of cutting it is concerned, the point is, if you take even a simple example like a disk, or you can take even the example of a circle. If you sort of poke a hole in the circle, literally that means you're removing a point from the circle. And if you remove a point, that thing literally opens up. So that becomes like an arc. It sort of looks like a shape like that, right? So that thing is no longer the same as a circle. So that's kind of the point. So if you are allowed to poke a hole, the circle no longer becomes a circle, because the circle kind of encompasses one sort of turn or something inside it.
Right.
You cannot shrink the circle by staying within itself. So if you are on a circle as an abstract entity, like an ant traveling on a circle, and the circle is your world, you would not know that the circle requires a plane to live on. You'll just be
Right.
going round and round, or either clockwise or anti-clockwise, and that's the only world that you can probe through your sort of intrinsic senses. Whereas if you make a puncture, then that circle basically becomes like an interval. It's just a curved interval. So if you
Absolutely.
start going at some point, you will just like drop down through that puncture that
Down
you
the
created. So
right.
I mean, these two will not be the same even geometrically or even in topologically, which we can like formalize and make sense of.
Absolutely. We have got a question which is a little bit different. Rajvardhan is asking, how do you motivate algebra? It feels very unintuitive.
Well, I guess yeah, Rajvardhan. So it depends on the context. So, for instance, if you read group theory, maybe some of you learned linear algebra before group theory. Some of you learned group theory before linear algebra. So I would say linear algebra is probably part of everything. So if you think of linear algebra just as pure algebra, as matrices, well, they are transformations on actual things, right? On planes, on the three space. So you can think of matrices literally not as a collection of numbers, an array of numbers. They're literally transformations, and you can study transformations on the plane and the three space quite geometrically. I mean, it depends on the approach. Similarly, when you're seeing group theory, typically you see group as a set with a binary operation. You check the group law, and usually you write down these tables, multiplication tables. But if you think about it, a group from a geometric perspective or even a physics perspective is basically thought of as a collection of operations which acts on a certain given geometric object, and it transforms the object in an invertible manner, meaning any operation that you do has an inverse. So this collection of such operations will be the relevant group in the context. So for example, on the plane, on the xy plane, you could have a reflection across the x-axis. If you do it twice, you don't do anything. So that gives you an operation which is of order 2. And you might say, well, this is a group of order 2 and I know how it acts on the plane. I reflect along the y-axis. A linear algebraist might say, well, this is a matrix. I know what this matrix is, right? But it's algebra and it's geometry at the same time. So it depends on how you interpret some of the aspects. But of course, algebra has a life of its own. So it's more to do with symbolic calculation, setup, and even more involved things these days. But yeah, I mean, there is a fair bit of geometry even in basic algebra when you see it. So field theory, for instance, has a lot of geometry going on. It's about symmetries of roots. It's not just solving polynomials and using radicals, although that's how it's often presented.
Absolutely. Thank you, sir. Thank you very much. Bishnu Prasad has got a question. Sir, I have a question that do higher dimensional spaces beyond the third dimension have any meaningful physical reality, or they are purely abstract concepts?
Well, Vishnu, so see, I'm not a physicist, but if you ask any modern physicist to do these kind of theoretical physics, string theory, gauge theory, quite often their world is either 10-dimensional or 28-dimensional in the setup that they phrase and frame things and expect things to happen. So they are dealing with supposedly some model of the physical reality of the world, but to explain all the physical nuances, they have to resort to a world which is much higher dimensional than the world we live in. So they do require a knowledge of what happens in these higher dimensional worlds. And mathematicians have developed, over centuries perhaps, like lots of theories of what can be said about these spaces of higher dimensions. So of dimension n, of course you cannot see them. It's very hard to sort of even imagine something in 4 dimensions, but you can still do calculus symbolically and arrive at certain results, recognize patterns and so on. But from what I know, there are models of physical sort of universes in string theory which are either 10-dimensional or 28-dimensional. So whether they are physical reality, that's a matter of, I guess, whether whatever they propose, whether you can actually deduce real life consequences out of it. But it's a valid theory in physics, and people, big names, have been working on it. So it's up to you at that point to say whether you'd call that physical reality or not. But it's unavoidable in a certain sense that you have to go beyond the dimension where you're studying things to sort of have a better look at what's going on.
Okay, that answers your question. Okay, sir, Uttam is asking, is it good to do bachelor's in statistics or in mathematics?
So this is like there are two different streams, right? So if you do mathematics, usually, uh, yeah, I mean, one avenue, if you're really interested and passionate and reasonably good at thinking about logical things, would be to pursue some teaching, research, and those kind of things. There might be jobs depending on what kind of applied mathematics you might do. And on the statistics side, certainly, if you learn your material in the course as well, you have a very good chance of getting a pretty good job, because statisticians are always in demand in India, abroad, everywhere. So there's always that aspect for in doing a degree in statistics. If you do it well, you could certainly also go into research. So nobody's stopping you from doing it. In math, probably one would expect typically it's teaching and research, and less of a job sort of aspect, unless you do things along the way, which is more fashionable, learn certain other things like coding along the way, combine it with some interest of yours, uh, things like that, or do some interdisciplinary thing with math and bio. So it depends, but statistics always has that hook that if you do it well, you'd get a job, certainly, but you might want to still do academia.
Right. Thank you. Thank you, Dr. Somnath. Jason is asking, is there any work being done on circumscribed tetrahedrons?
So I don't know much about what you mean by circumscribed tetrahedron. So, I mean, tetrahedrons, as I understand, is this three-dimensional object, right? It's one of these regular polytopes. So there are, see, I mean, I don't know the context of the question, but there are many such combinatorial questions which are easy to state and might be open. So if you're interested, you can look at this like fairly classical problem called the sphere packing problem and see how much work has gone into it, and people have worked on it for a long time and then made breakthroughs, and it has been stagnant for a while before people made other breakthroughs and so on. So that would probably go into combinatorial topology. I mean, the kind of questions I believe you're asking. So it depends on the context. So easy to state questions need not necessarily have an easy answer. It might be that things which were known were done, and then things have stopped for a reason, because either there's no refined theory which answers the question, or the current methods are not enough to lead to new results. So until somebody comes along, maybe you can
Yes.
like
Come up with something
yeah,
new.
come up
Yeah.
with a new idea which will help.
Absolutely. Absolutely. We have got a question, sir. Apart from topology, do you work some other problems like Navier-Stokes equation? I personally really like it.
Yeah, so I'm vengeance. So the point is, usually Navier-Stokes, I mean, it's one of these millennium problems, but even apart from that, it would require a reasonable understanding of partial differential equations the way it's stated. And even then, you have to understand why the current methods are not enough to make any kind of progress. And many big names have been working on it. Uh, over decades. So it's an area which I know very little about. So I have taken one course in partial differential equations when I was a PhD student. I liked it, but it's not what I do currently, and it's definitely very far off from what I do. So even to make any reasonable claims about the status of the problem for me would require me to read through the huge literature that's already there, because it's a topic of interest to many. So many analysts have worked on it for decades. So so you can even ask, it's like how my advisor used to say that everybody knows how water flows. You ask anybody on the street, they know how water flows, right? So how hard can this be? But we are flying in aeroplanes all the time, and nothing chaotic happens. Let's put it that way. But we still don't know whether this thing has a solution, right? Navier law. So
Yeah.
yeah.
Yeah, I got your point. Rajavardhan has got a very good, very pertinent question, but I would request Rajavardhan to wait because I am now pregnant with many ideas, sir. And my question to you would be that Poincare conjecture, I think, is something which is related to topology. I would
Yes.
humbly request you if you can explain to all of us, maybe technical or in a non-technical sense, what is Poincare conjecture, why it has been so difficult to prove it, and Grigori Perelman used something which is called a Ricci surgery. I know it is a very technical thing, you might be angry on me, but still we would like to know because you are the right person, so many years of experience in topology. If you can just explain the Poincare conjecture and a little bit how Perelman used the Ricci surgery to prove the conjecture.
Yeah, okay, so I mean, my knowledge about Perelman's proof is next to zero, because he uses so many techniques outside of topology to prove an inherently topological statement. So Poincare conjecture. So at the heart of it, basically, we have these standard shapes called the spheres. So for those who have not seen it, spheres would mean you are in some n-dimensional space, and I am assuming most of the audience members have seen calculus. So n-dimensional space means you have x1, x2, xn. These are the n directions in your n-dimensional space, n-dimensional Euclidean space. And inside that, you can consider vectors of length 1. So that would be the sphere of dimension n minus 1. So for instance, in r cross r and the xy plane, if you look at all unit vectors, they are of the form x comma y such that x square plus y square equal to 1. So that's the circle. And a circle, if you walk along the circle, it has intrinsic dimension 1. So we call it a sphere of dimension 1. Similarly, you go to R3, the three-dimensional space, x, y, z, and you look at the unit vectors in there, they form what's called the two-sphere. Okay, like the surface of the earth, if you want to call it that. So similarly, you can go in high dimensions and look at the unit vectors there. So Poincare conjecture, I think here the initial thing that he stated was slightly wrong, and then he realized it and he rectified his conjecture. So what he said was, if you have so any shape which is locally has n degrees of freedom is called an n manifold. Okay, so for example, anything which locally has 2 degrees of freedom is called a 2 manifold. So anything which has locally 3 degrees of freedom is called a 3 manifold. So this unit sphere in R4, which is x1 square plus x2 square plus x3 square plus x4 square is equal to 1, this shape, this is locally three-dimensional, because once you fix x1, x2, x3, I can ascertain what x4 is up to a sign simply by solving this quadratic, right? So it has locally 3 degrees of freedom, so it's a 3 manifold, and there are many other 3 manifolds. Okay, so R cross R cross R, the usual x, y, z space is a 3 manifold because it has globally 3 degrees of freedom. So there are many such 3 manifolds. So Poincare conjecture stated in this form would say that if you have a closed 3 manifold, meaning it's sort of not unbounded like R cross R or the XYZ space. It's sort of contained in some some finitary kind of shape. So if you have a closed 3 manifold and it has no boundary and it has no non-trivial loops. So what do I mean by non-trivial loops? I mean, take any loop which lies on the shape, in this case a 3 manifold, and you should be able to deform this loop continuously to a constant loop. So if you imagine the usual circle on the plane, namely the set of points x square plus y square is equal to 1, you can take the circle itself as a loop adjoining the circle itself. And it's pretty clear that you cannot contract that loop to the constant loop because it's stuck along itself, and you cannot go through the inside because the inside is not part of the circle. However, the same loop, if you imagine happening in S2, which is x squared plus y squared plus z squared is equal to 1. So now the loop is on the xy plane, so that's the equator of the sphere, right? And the equator of the sphere can be shrunk if I simply move up according to latitudes and shrink it to the north pole. Okay? So the equator, which was earlier stuck along the circle, is now being able to we are able to continuously deform this and get to a constant loop. So it turns out that all these higher spheres have this property that any non-trivial loop can be deformed to a point. So Poincare's conjecture was, if you have a closed three-manifold and any loop on this three-manifold could be deformed to a point, then this three-manifold has to be the three-sphere, meaning it has to look like x1 square plus x2 square plus x3 square plus x4 square is equal to 1. Okay? So that was his conjecture, and it was open for a long time. Various people took stab at it, used their own methods, and transferred that into other kind of equivalent formulations and so on. So yeah, is that good enough for what the conjecture is? Are there any questions before I go on to the second part?
I think that was perfect. Now, what I wanted to ask, sir, is that this is purely a topological problem.
Yes.
Okay.
It is.
So what Grigori Perelman did is that I mean to say, it was a conjecture. That means it's a kind of a statement which was not mathematically proven.
Yes. Yeah.
Okay. So this Ricci flow, or does this come under the area of topology, or is that got physics in it?
No, so Ricci flow would I mean, I would say it falls under differential geometry or geometric analysis. So it's a separate field. So what it is so I could give a very sort of, okay, it's not exactly Ricci flow, but like a basic version of it. If you imagine you have a loop on a non-intersecting loop on the plane, and if you allow some sort of force to like straighten out the loops, the loop could be very sort of like zigzag, but it has no self-intersections. If you allow some sort of force to clean up and make the loop round enough, you can imagine some force doing it, like the inside parts just get pushed outside, the really loopy outside part gets pushed inside, and so on. So somehow with time it deforms to some circle. So a Ricci flow, very, very vague and naively speaking, would be a flow that you define on a manifold, but for that you need to have a notion of what's called a Riemannian metric. So you cannot just work with a manifold. The manifold has to have a Riemannian metric, and once it has a metric, you have all these various curvatures. So there's Ricci curvature, scalar curvature, there's Riemann curvature tensor. All of this is part of classical differential geometry and Riemannian geometry. So what this Ricci flow does is, it's an equation which says how the Ricci curvature should change. So Ricci curvature is a type of curvature which says something about the manifold. In low dimensions, Ricci curvature says quite a lot. In high dimensions, Ricci curvature may not say much about the shape at all. So it's a quantity assigned at every point of the manifold. Okay? And so you have a function defined at every point of the manifold by computing this thing called the Ricci curvature. And then there's the Ricci flow is an equation which saying how should this Ricci curvature change, which means the manifold sort of let's say stays the same, but the metric which gives you the curvature should deform with time such that the Ricci curvature equation actually is satisfied, maybe for small time, maybe for large time, and maybe it blows up, maybe there are singularities happening, and so on. So the point was, there's this thing which was originally due to Hamilton, because he had some insight that maybe this could be used to do interesting things. And so Perelman actually followed this program through, and you do have to show that if singularities develop, then you can sort of do some sort of surgery, and you have to control them and run this flow again and sort of do it so that you get in the limit what you want. So ideally what you want is, if you imagine that squiggly loop thing that I just said, if you run some sort of an analog of Ricci flow, you'd imagine that you have a very squiggly, non-intersecting loop on the plane, and you want to sort of poke your fingers from the inside out, outside in to make it like a round circle. And you can imagine doing it in practice, but you need a equation, a flow equation with time which does that. So you'd want to do a similar thing for even the two spheres. So you could imagine a golf ball which has been battered very badly. So it'll have a lot of pock marks, dents, and so on. And you can imagine like pushing from the inside and pushing from the outside at appropriate places to make it perfectly round. And you can in fact do that using Ricci flow and so on in dimension 3, which means for S2 you need some estimates. And in fact now there's books about it where one can read these things if you have taken a course in differential geometry. The case for the higher dimension, which is dimension 3, that is S3 in R4, is actually much more challenging because the equation runs into problems. You need singularities, you need to sort of combine things other than just geometric analysis or a knowledge of Ricci flow. So Perelman kind of, because maybe he was from the Russian school, you had all these knowledge that he
Yes.
has learned. He combined everything, and then so what he proved was, to my understanding, was more than Poincare conjecture, because Poincare conjecture at a later stage was subsumed by what's called Thurston's geometrization conjecture. And so Perelman contributed a proof to that, to my understanding. I haven't read any of these proofs because after a point it's quite technical. But so he proved that as a particular case was this Poincare thing, which was saying that if you start off with some appropriate manifold which has some things similar to the sphere, you run this Ricci flow, you can adjust the places where it might run into problems, run this over and over again, and then it should give you something which is, let's say, uniformly round. But anything which is uniformly round and of that type with the right shape is S3. And so that's kind of how I proved it. But yes, it's very surprising even now that a purely simply stated topological thing still has no purely topological proof. Uh, it needs like so much machinery developed for other
Absolutely. Yeah.
reasons,
Yeah.
not for this reason.
Absolutely. Okay. Thank you, sir. Thank you very much. That was good enough. We all understand Perelman to be a great genius, but in order to know actually and appreciate that, we really need to go to that level of mathematics. True. Sir, we have got few questions coming up quickly. Rajvardhan is asking, how do you visualize complex shapes, spherical surfaces?
Uh, so spherical surfaces, you mean if you mean spheres in higher dimensions, uh, I mean, there's no direct way to visualize. I mean, you can visualize the two sphere in R3. I mean, the usual balls that we play with, like the surface of a football and so on. And other two-dimensional shapes, like if you're eating a vada, or if you're in the abroad countries, you'll be eating a donut. The surface of a donut or the surface of a vada, that's a two-dimensional thing. So things like that you can imagine. But beyond that, you cannot imagine things which require 4 dimension to visualize. So as you said, the three sphere S3, which is x1 square plus x2 square plus x3 square plus x4 square equal to 1, you cannot imagine it in the space we live in because it requires 4 coordinates to define it. So that's one issue. But then there's another issue that sometimes you will have things which you can see in the plane or in your 3 space, but they come with geometry, meaning that they are curved in a certain way, and we cannot visualize them either, because to imagine them curved in our space time, it's not possible. So what we do is we resort to calculus. We say that, okay, I pretend that this is lying in the sheet of paper, but the sheet of paper is flat, but I know what the calculus is on this object which lives in the sheet of paper. The calculus has a certain bending, so I'll not pretend that it's the same bending as a sheet of paper. It has its own sort of curvature, but that's not an intrinsic way of studying objects. But it's the only means we have, so to speak, because it's very hard to intrinsically imagine, say, an n manifold or a geometric object. Meaning you have to imagine you're living inside it, and then you're probing the space from inside, not from outside, which is what we do usually. When we say a circle, we imagine the circle on a piece of paper, and we are looking at the circle from afar, not by staying inside the circle, right? So there's a difference in that perspective.
important. Again, I will like to take a note of what sir told, that whenever we are imagining a circle, we imagine it right from the top, that the circle is on the on the paper. But typically we should imagine that we are lying inside the circle, and how does the circle look from? Yes. Yeah, thank you very much. Okay, Abhijit Pal has got a question. Sir, I want to know, how can I learn the concept of topology to understand deep learning? What are the relevant literatures?
Okay, so so Abhijit, yeah, so I know that, I mean, these days a lot of topology is being used for like deep learning, persistence homology, and other such things. I myself have absolutely no idea about deep learning. What I would guess is any of these applications of topology to these, uh, I mean, at least more or less new fields would require you to know basic topology and perhaps to an extent basic algebraic topology really well. So basic topology means a typical course where you learn, uh, you know, uh, like the relevant chapters from a standard text, and then algebraic. Sometimes, for example, in the areas that I kind of know a bit about, you do need things like homology and cohomology, and maybe some version of discrete Morse series. So that falls under algebraic topology. So maybe you need to know basic topology certainly well, and then a bit of the relevant things from algebraic topology, which fits the needs for the things that you'll be working on.
Thank you very much. Okay. I am Vengeance is asking, in classical relativity, we see space as something which has continuity and smoothness without involving infinities. When we quantize it, does it really get to discontinuity? It is the main problem of IgG. IgG, I mean loop quantum gravity. Does it happen at the lowest universal scale, the Planck scale? Just curious about things. Sorry to involve some physics in it.
No, so it possibly is a good question. See, I mean, I hardly know anything about loop quantum gravity. Uh, so, I mean, there is this thing called quantization which physicists do, and it's like a mechanism for them. I understand very little of it. The cases in which I do understand it is probably purely mathematical and has no relevance in physics. It will be either related to deformations of structures and so on. Uh, so I probably wouldn't be able to answer anything interesting about or anything intelligible about what you asked. But I do understand that when you talk about space time, you basically are thinking of R4, but you're not thinking of R4 as the 4 space literally with the metric. You're thinking of it as R3, and then there's a time parameter, right? So one thing that I've personally had issues with and then had to come to terms with is when physicists sort of say this, they say that it's a metric space, but it's just that the metric has a negative sort of signature because it's x squared plus y squared plus z squared minus t squared. So then you can have vectors of negative length and so on. To a traditional mathematician, you would not put it this way. You'd say that the topological space is R4. It has the same topology as R4. No questions there. Now you're somehow putting an inner product on R4. The inner product happens to be not positive definite. And then you sort of play the same game that you do in Riemannian geometry, except that you do not necessarily have positive definite inner product. So the metric or the Riemannian metric is not a Riemannian metric anymore, but you can still do certain things from Riemannian geometry back in this setup. So that would be something that I would emphasize if you're trying to learn this and at somehow have conversations with a mathematician. Uh, this would be a point where you have to sort of like jump the bridge, shake hands, and then you are talking about the same thing. Okay.
Okay, this is a question which Vishnu actually asked. Mainak is again asking, what is the application of topology? Can we use that in computer science?
So okay, I can so I can only mention let's say the things that I know of. So in physics, for instance, so topology, if you ask me just to add this in, broadly speaking, you might say it's broken up as currently understood into, let's say, four subfields. There's the general topology, which is also called point set topology, and not very much pursued as far as research is concerned. Then you have combinatorial topology. So these circumscribed tetrahedrons and these polytopes and all such things, configuration spaces, they are all part of the combinatorial topology to an extent. And then you have algebraic topology and differential topology, and maybe we'll get to each one of them at some point. So both algebraic and differential topology is used very much in gauge theory, which is something in physics where you study these anti-de Sitter spaces, you study Aronoff bomb effect, all these things. It's used in quantum computations. It's used in computing and evaluating multipartite entanglement entropy. In studying topological insulators, it's certainly used in string theory. And so that's one aspect of how it might be used in physics. And this is theoretical physics, of course, but down the line some of these would get translated to actual tangible things via engineering and other means. Okay, and that's how things goes. I mean, things in math might take a few decades to percolate down to physics, which might take a few years to percolate down to some tangible real things. So I know, for instance, I mean, there's this mathematician Robert Grist. He's an algebraic topologist. He has been using his expertise to improve sensor networks, configuration spaces, and robotics. Okay. And I mentioned persistence homology earlier. So people have used persistence homology, and by people I mean mathematicians and computer scientists, to improve image recognition software. And so the ideas are inspired by classical Morse theory, which is a part of differential topology. In sometimes topology helps understanding the molecular structures in chemistry better than you do using just usual chemistry lexicon. And if you want to sort of think of other like pioneering things, so topological insulators, which is a very big thing these days, a lot of people are working on. If you can build a literal topological insulator which works the way it should be, it has already pioneered, electronic devices in the sense of spintronic devices and quantum computation. So there's, at least these are the ones that come to mind. So I hope that answers your question.
I think you have quite given a very wide spectrum of the application. Okay. I don't know, sir, is this a very technical question in this podcast? I mean to say we can take it. Abdul Halim is asking, Yau's conjecture, the first eigenvalue of the Laplace on a minimal surface on closed minimal hypersurface in sphere Sn plus 1. Would it be possible to say any sketch of its topological aspect?
Abdul, yeah, so I'm sort of just aware of Yau's conjecture, but I certainly would not know anything to comment on it. So it's a question. See, this eigenvalues of like Laplace operator or Laplacian has been of interest to many. And if you really want to sort of read a classical article, there's one called "Can You Hear the Shape of the Drum?" I would highly suggest you read through it. People have been interested in Laplacians, for a long time, like differential geometers, topologists, because it's such a central operator. It's an elliptic operator. But I certainly wouldn't know anything to add to what you might see otherwise in an article or a paper.
Can you hear the shape of the drum? This is a book, right?
Yeah, I guess so. So this was I'll have to check. Yeah, so this is probably a maybe a paper or something, right? But if you search for it, you'll get to it. It's supposed to be a like a. So I think it's an article. So can
Okay,
you or
fine.
can
Not a
one hear the
problem.
shape of a drum? But maybe people have then worked on it. But I'm referring to the original one. I think by CAC or something.
Okay.
Yeah. Yeah.
Rajvardhan has got a question. As an undergraduate student, how do I know the branch of mathematics should I pursue for projects, research, etc.? Because I like almost all branches of mathematics. It is difficult for me to decide.
See, as an undergraduate, by that I mean, I am hoping you mean BSc. So if you are doing a BSc, BMath, or whatever, a 3-year equivalent, you would have to learn the basic subjects really well in any case, because for instance, basic linear algebra is used everywhere, even outside of math. Basic calculus is going to be used everywhere. Even if you're not doing sort of analysis, you will need basic calculus. You need basic algebra also to an extent. So these you have to learn, and usually they come in sequences, like analysis 1, 2, 3, algebra 1, 2, 3. You have to learn them very well as it is if you really want to pursue maths. Once you go into your masters, you'll probably have some course choices of electives or some independent study. So there, I guess the best thing would be to, it's not like you like everything. It should also be that you are able to solve problems, you're able to think through certain things in a different way, and you're able to, and you like thinking about things on outside of the course curriculum. So if it's a topic for which these things happen for you, and you're of course doing well in the course as well, then maybe you can think of doing some project or independent study or an elective in that. If you have two such choices, do one in both and see which one you like them. At some point you have to make a choice, you cannot sort of pursue both, but keep these things in mind, and I think that will help you sort of whittle down the choices to maybe two or three or one. If you're lucky, you'll still be liking, so for instance, if I say in my case, when I was doing my undergraduate and then my masters, I still I tried learning a lot of algebraic number theory and algebraic geometry. I still like them, but it's something that I haven't pursued in a while, and it's probably going to be a while before I can get back to what I learned. But so you might still like something, and you might still attend occasional lectures and find the magic in it. But at some point, you have to pick and choose, because even within that specific topic, there's so much to learn. So you just have to like just get down, get dirty, and sort of be able to like do the details if asked for. So I mean, even that takes time.
Absolutely. Thank you very much. Dr. Somnath, I was really curious to know that you worked with the famous Abel Prize winner Dennis Sullivan in Stony Brooks doing your
Yes.
PhD. Can you share some experiences and what makes Dennis Sullivan so great?
Well, so yeah, so I guess it's hard for me to add to things which other people have already said. And if you look at the citation by the Abel Prize committee and so on, they've already said it. My experiences with Professor Sullivan. So I think now I call him Dennis. So it has been that he is somebody who is not specifically, at least when I started working with him at Stony Brook, he was around, I think, like late 50s, early 60s. Okay, anyway, so he was very much not too keen on the specific of the details, because from his perspective, it was clear that a certain result should have a certain structure and a certain pattern, and if one nails that, then one can work through, maybe even work backwards, and like fill in the rest of the things, which is not how me or maybe many of us learn how to do things in our bachelors in school. You sort of do things in a certain orderly fashion and so on. So that was a learning experience, that to be able to sort of think, assuming certain things might happen, think beyond, and then sort of like work backward. I think physicists to a large extent do think in this manner, and it has its own pluses and minuses. So that's one. And the other thing was that like Dennis was usually quite flexible in terms of what you could ask him. He was very approachable. You could ask him a question outside of topology, from analysis, from dynamics, and he would be curious and still interested in thinking about these. Of course, uh, I mean, from me as a PhD student, I had a certain timeline within which I had to graduate and so on. So the number of such questions I asked him sort of went down as the years went by. But there was one amazing thing, that if you can catch hold of him, anything mathematical, even if it's supposedly a very elementary thing, if it's interesting, one, you can ask him and he would be curious and he would sort of think about it. So I still remember that he used to encourage us to go to physics seminars in the hope of learning some ways, or at least getting to know what are the kind of ways that the physicists kind of do mathematics, so that they come up with conjectures and theorems which mathematicians often have a hard time solving, or even going to seminars in dynamical systems just to see what kind of things they're doing. And so he used to do that. So that was an eye opener, because initially you'd think, okay, I'm doing this and this is what I should do, why bother about other things? And so he had a like a very, very open and flexible mind, so that was helpful. But yeah, so it was a really rich experience, because you kind of see often how he thinks about things, and it's not usually what's in the textbook or in a paper or something. I mean, he has his own way of thinking, certainly. So you can at least get inspired by it, rather than sort of
Absolutely.
take it the other
Getting
way.
inspired, right, right. So, Dr. Somnath, one question which I think will be very common to all the people who are watching. We understand that topology is a kind of a counterintuitive phenomena which generally doesn't match the way that we think. So before going and embarking into topology, I always make videos, and I'll always tell that in order to go to topology, first thing that you probably need is to how to write or how to understand a proof driven mathematical system, any kind of a proof that you can properly write. And you need to have a mathematical maturity before going into topology. Now, you being an expert, tell us that what are the mathematical prerequisites that a person needs to know to understand the basic topology, and what would be the approach that I need to know this, without that I cannot go into topology? What would be the basic foundations?
So I guess yeah. So one okay. So I would put it this way. So see, I would say, I mean, most people would come the time that they see topology in a BSc or an equivalent course, you basically have seen like the analysis on the real line. So basic analysis on the real line, meaning limit sequences, convergence, maybe even compactness, but you kind of use the notion of metric spaces already. So once you have seen that, I guess the point would be, then you want to, if done correctly, you would want to generalize the notion of continuous maps and other kinds of things, but now to other sorts of spaces, and you do not want to resort to having a metric. So one usually sees metric spaces after this in a typical topology course, and then you go on to a general topological spaces. So the whole point of constructing topological spaces was to study these abstract notion of so-called continuous maps without resorting to having a metric, but having the bare minimum, which, as we understand now, turns out to be the notion of open sets, and a collection of open sets forming what's called a topology. So once you have seen that, I guess that's usually so. Of course, as you pointed out, one issue is you might be tempted to use pictures as a proof, and often pictures are misleading because pictures can be counterexamples to standard things. But if you largely, let's say, keep the analysis on R or analysis on Rn in mind, which you can do using metric spaces, sequences, and various other means, you can always use that as an anchor. Like whatever you're doing for abstract topological spaces, whether it's true or not, or what you proved is true or not, if you put in a possible Rn as a test case, and if it fails or you have other ways of checking it, then you know that your proof works or it doesn't. So it will take a while to get used to the proof language, or even the concept of open sets having certain properties, and the concept of a topology, because it's an abstraction, but it's an abstraction sort of like crystallized in a form which has stood the test of time. But I personally try to use calculus in R and Rn or analysis in R and Rn as sort of an anchor to always like uh, like if somebody says, okay, how do I prove this? Well, if you cannot prove it for an abstract space x and y, can you prove this for R2 and R3, for example? There you can use sequences and all that. So if you can do that, then maybe think, what can I get rid of if I don't want sequences? What continuity arguments do I use? So, and typically, if you look at a good book like Muntres, they'll say why open sets are equivalent, because you can replace the epsilon delta definition with open balls, and then you can say, okay, I can disregard open balls, they're too rigid, I'll simply work with open sets. And so there's a clean transition between the usual definition and the more abstract definition. But it has its advantages because you don't necessarily have to choose a metric to work with. There's a plethora of metrics which choose just one as long as they give you the same open sets. So that flexibility opens up a lot of avenues. So you're muted, Shona.
Oh yeah, I'm so sorry. So most of the cases we see that the book of Munkre, etc., which starts with topology, it starts with using the set theory. So is
Yes.
it any reason that you told about differential equations, etc., but primarily the main predominant factor of the mathematics of topology is set? Why it is so? Any reason that you can tell us?
Uh, mm, Not particularly, but you will see set theory, I guess, pretty much in many things. Like, so if you're doing probability, for example, apart from basic probability where you have finite outcomes and finite sets, you would be dealing about sets. I mean, that happens to be sort of the current foundation of mathematics, that everything will be built out of sets. So even in basic probability, you'll have to look at sets, and then you'll have to throw out certain sets because you want to talk about assigning a measure to every set and so on. So set theory, as we understand, is the foundation of any sort of like subdiscipline of maths. Even in algebra, you'd say a group is a
Right.
set equipped with a binary operation. And so there, if you want to go deep into set theory, you might say, okay, what do we mean by set of all sets? What kind of axioms give us sets? So there's a whole story to that. So you can go in there, but it's better to sort of assume that, okay, there are these things which we want, and there are these sets which we cannot make sense of, like set of all sets. And there are certain axioms which, if you have taken a course in set theory, fine. If you haven't, you can treat it as a collection of objects, and unless you run into an issue, you can just treat it like that. So not all collection of objects are going to be called sets, but anything which is, which can be expressed in some notational form or the other, for the most part. So we pretend that we know R when we are talking about analysis, but one would ask then, how is R constructed, for instance? Then you have to start with rational numbers, but then you have to go back to integers, and then you have to go back to natural numbers, right? So historically, or at least the foundation would be that you start with n, and then z, and n is natural, z is integers, q is rational numbers, and then somehow you get R. But when I sort of I've been teaching a first year course, and I have had students ask me, why is n natural? I said, well, because he's like counting 1, 2, 3. He said, yeah, I understand that, but why should that be natural? So then I said, there's a solution for you as well. If you don't think natural numbers are natural indeed, then you can start with the empty set. And the empty set, there's no argument. There is one empty set because it's a set containing nothing. You and I both have the empty set. So then I said you can reconstruct all of natural numbers purely from set theory from the empty set. So if that makes you happy, fine. Whether your friend would call it natural, that's up to you. So then he said, okay, I see your point. So
Yeah,
there's a
that
whole
is a wonderful
construction,
way. Yeah.
but you can still say, I'll assume what real numbers are, and I go with the analysis metric spaces, and then I go into topology, and that's a perfectly valid way to do it. You can read set theory a bit later if you're interested.
Right, right. Sir, we are coming to the close of today's session. I will take few questions, but one thing which keeps me wondering is that, so in case of physics, for example, I mean to say we are trying to achieve a theory of everything where quantum mechanics, relativity, Maxwell's equations, etc. And are trying to put it into one single equation, for example, and get a unified. Now, what I can understand from a limited knowledge is that, as you rightly told, that geometry has got a notion of metric. There is a distance, there is a metric involved in it. So topology, I can talk, is also a kind of a search of unification, where the notions of distances are not there, where the notions of points are not there, but where objects can be, defined on a very, very fundamental way, where obviously the distance, the Euclidean notions are all there, but those shapes which have a strict notion of angle, length, and all those things can be now deformed into a lump. Say, for example, a clay lump. Now, that lump contains all the Euclidean objects, but that can be again extended with the certain mathematics that you can see. This is an Euclidean object, a triangle, an angle, etc. But again, it can be formed into a lump, which is
Yeah.
explained by topology. So, is it true that topology is trying to get a meaning or a kind of a unison of all the geometric distances into one single framework?
Uh, so I guess it kind of depends. So one way to answer this question is to say that typically if you are talking about geometric objects, I mean at least the ones geometers care about, or people in physics care about, let's put it that way, would be what are called some versions of what we talked about, n manifolds or 3 manifolds, or certain degenerations of manifolds of higher dimensions. So those are still somewhat special compared to the kind of spaces that topologists think about, which contains a huge amount of spaces which are not even of that form. So that's already a big difference. And so topology on the one hand, so the point is, again, you are trying to ascertain whether two spaces are equivalent to each other via these allowed deformations. There's no notion of distance, so you can stretch, twist, bend, and you're trying to let's say get, if possible, a comprehensive list of invariants. So usually there's none. So what you do in practice, let's say in algebraic topology, is you say, okay, given a shape, a geometric object, I assign various algebraic invariants like groups, rings, or certain polynomials or certain numbers. And then I ask, okay, if I can calculate some of these algebraic invariants, presumably because the algebra is easier, and compare that with the same list of invariants for the second candidate space, and if I know that two of the so-called invariants don't match, then I already can prove that the shapes are not topologically the same. And so, in particular, quite often you can translate it back to saying that the shapes geometrically will also not be the same. It's not always the case. So that's how algebraic topology comes into the picture. That so at the end of the day, you want to distinguish shapes. Let's say they're not rigid, distance specific, but how do you do them? You
Yeah,
assign
yeah,
certain things which you can calculate. Presumably,
absolutely.
you can calculate the easy ones. If that doesn't distinguish, you have to do the hard work. If it does, then you're done. So then you're happy, and then you go back to the geometer
Yes,
friend and say, okay, I've computed this for you, and that solves your problem.
yeah,
So yeah, it's what it is.
absolutely. We take one last question from Priyo. He says that what is embedding class 1 and 2?
So I don't understand the terminology class 1 and 2. So there is a notion of embedding. Embedding typically means it's embedding of a manifold inside another manifold. And these embeddings you can characterize by their regularity. So if you want an embedding which is of class C1, if that's what you mean, that means the map, it's a I mean, it depends on the context. So an embedding it could be a topological embedding, just a map which is a homomorphism onto its image, and then C1 means that the map is C1. Class 2 or class embedding of regularity C2 means the map is at least twice differentiable and all the second partials are continuous. So I don't know if that's what you mean by an embedding of class 1 and 2, but embedding is usually between manifolds or things which are locally n-dimensional, and you're looking for nice maps between one locally n-dimensional space inside another m-dimensional space. So for instance, the circle is embedded in the plane because you take the abstract circle and you realize it as cosine theta sine theta. So that's a smooth embedding because you can give both a smooth structure, but the square is not a smooth embedding.
Absolutely. Sir, these types of topology, when we talk general topology, like point set topology, algebraic, then we have a geometric topology, homotopy theory, these things. So, are they basically tools of defining the same concept of topology in different contexts?
Not quite. So, for instance, as I said, broadly, I would say like there's algebraic topology, differential topology, let's say combinatorial and general. So, homotopy theory is I would put it this way: homotopy theory is a subfield of algebraic topology, and it studies spaces by other means. It's not studying. It also studies spaces by using algebra, but algebra of a different kind. Uh, Yeah, so geometric topology, I would say one might put it inside combinatorial topology or club it with itself. So that's designed to understand certain low-dimensional spaces. The techniques are very specific to that, to my understanding. So they're all like subfields, and they're all not always catered to study the general class of spaces. They might be catering to studying knots, for instances, or studying certain kinds of four manifolds. And so the theory is only in place for that, and that's fine if it can completely classify or to a certain extent characterize these like subclasses of spaces you're interested in for various reasons.
And so I saw various videos in YouTube that one professor, I forgot his name, uses paper foldings, etc., physically to demonstrate these shapes and structures. So can topology be taught in a using objects in the class?
You can. So for surfaces, you can. So surfaces meaning things which are locally two dimensional. You can use like these foam sheets, and you can ask them to cut into small triangles, glue them, and build things, and then count and see that the Euler's theorem is true. V minus E plus F is true. Or things which are two-sided, make them color and see that okay, you really need two colors versus one color. So you can do this thing called cut and paste topology that will certainly give you an intuition and things to what's going on. The formal language you can sort of do once they have seen a bit of actual topology. I mean, there is a formal language, but you have to like learn the language first. So I have done that with some like reasonably smart high school students when I was back at Stony Brook. That they had 8 classes, and their whole point was to do this thing hands on. So one very good experiment for those who have access to bagels. So it's not good to do it with vada because it's usually quite oily. If you have bagels, try to cut a bagel, slice a bagel so that it becomes linked. Okay, if you slice the bagel in the usual way, you just get two halves, and that's not linked. So you can cut a bagel so that it becomes linked. In fact, if you search online, you'll see that there's an article by the person who sort of did this first, saying the mathematically correct way to eat a breakfast. And his intention was you get to put more cream cheese if you cut it this way. So it's a win-win situation, but cutting it is more delicate. So there are all these things you can do hands-on. Then you can say, okay, you need to know algebraic topology to explain what's going on. So they're curious, hopefully they'll take a course in algebraic topology later on. But for two dimensions you can certainly do things to an extent, but it may not be part of the usual curriculum, unfortunately. uh, so yeah.
Yeah, I think I just got that link which you have just told. It is called Mathematically Correct Breakfast. And I'm just sharing the link over here so that you can, even I would be very interested to see this because I have never seen that one. We have from Mathematically Correct Breakfast. Yeah, I mean to say that is wonderful. Last question, Professor Somnath, is that what would you suggest as the first book to take up in topology for students who are taking up topology? You told that differential geometry would be required, set theory and analysis after that. What would be
No,
the
no. So,
first?
yeah, so differential geometry comes later, but you would need, if you have seen real analysis in one variable, that would be helpful. Obviously, set theory. But beyond that, I guess, see the books that I kind of learned from. There's this book by James R. Munkres called Topology. I think it has many editions. You can look up the current edition. There's a book by George Simmons called Introduction to Topology and Modern Analysis. So he kind of does a bit of both. And then there's this other book which I personally like very much. It's by M.A. Armstrong, called Basic Topology. So he goes into algebraic topology at the last bit, but you can pick up any of his books. He has a book on group theory. That's an excellent book for, and somebody initially was asking why is algebra sort of not geometric. So if you read Armstrong's book on groups and symmetries, you would be a convert. I mean, he introduces group theory and does a whole bunch of group theory, but everything he does with is solids. He'll give you a solid in one chapter, do all the symmetries, and then he'll introduce a theorem. So he has a book also in topology called Basic Topology by Armstrong. That's also a like fairly good book. There will be good books by authors in other languages also, in other than English. I am not aware of them as much
Right. Right.
because I haven't used them as text to teaching students.
Yeah. Yeah, Mooncrest Boost is actually a classical. I also followed that. And I've given the link for George Simmons' book. This question is that I really cannot understand this, sir. Embedding class 1 equals to Euclidean space without self-intersection. Class
Okay.
2 is of controlled singularities or intersection. Does it mean?
So Abdul, I guess if you are saying Euclidean space without self-intersection, that so usual embedding is that. I mean, embedding doesn't have a self-intersection by definition. Immersions might have self-intersections. Okay, so at least that's the standard, universally accepted terminology. So if you're saying embedding to a standard mathematician, embedding means no self-intersections. Immersions can have self-intersections, but then you have to understand what is the singularity. So singularity is not really a well sort of classified and easy to state thing. Like there are these many singularities. It's a whole field and it depends on the context. So when you say control singularities, you want us to specify what kind of singularities you're allowing for an immersion to have. And usually, there's no like list that okay, these are all the singularities and so on. It depends on the context. People study singularities for complex curves. That leads to a whole bunch of things which are connected to physics called mirror symmetry. People study singularities elsewhere. So so I guess what you're looking for is embeddings, which is embedding of class 1 according to you, and immersions, which can have self intersections, but immersions are studied for what they are. You don't have any control on how badly it self intersects. But if you want, then you have to put some control on what kind of singularities you're allowing, and that depends on what kind of spaces you're mapping in, one dimension, two dimension, and so on.
Okay, Professor Somnath, thank you, sir. Thank you very much for this podcast because I was really waiting for this podcast. Very rare to find a person like you in topology, and you are teaching already in IISER Kolkata. So I think that the students are very fortunate to get a person like you who explains things so easily. Any last minute message, or those who will be taking up topology in the upcoming career, watching now or maybe later, anything that you would like to suggest, because you're the best person to, they are the expert on this.
Okay, no, I mean, yeah, I can only just say some. Yeah, so first of all, I guess, yeah, thanks to Shaunak and to everyone who tuned in, for like a nice set of questions. So I can only go by my experience because I've also learned a lot from teaching and from the students. So the best thing is whether you're like pursuing topology or any other field in mathematics or science for that matter, you have to be open to learning new things and not be dissuaded by how a particular subject is taught by a particular professor. So you might have a course in analysis being taught by a non-analyst, and it might not be taught the way you want. You might still like analysis, but maybe what would happen is because it's not taught the way you like it, you might get dissuaded. So all I would suggest is, if you really think you are doing well in a topic, you like the topic, stick to it and keep an open mind, because you might end up liking some other topic parallelly, and it's not a bad thing that you have liked something for a few years and then all of a sudden you like something more. We all do that in life. So keep that option open. You never know what you might end up liking more, even after liking something for 5 6 years. Uh, so
Absolutely. Thank you. Thank you, sir. I would also request Professor Somnath that you can email me the links of your published, papers in different magazines, because as this video will be later also watched by several individuals, I would like to put all the links, all the citations that you have at the on the description of this video. And I will also requesting that anybody who is interested to know more technical about Somnath sir's technical papers, writing, citation, I will be putting it by one in 1 or 2 days. It will be done. So you can go ahead and read his papers on topology and various areas of mathematics. So you can just pass on to my email the links so that I can put it up, and this will be something good for the future generation also to read on your works.
Okay, I'll surely do that. Yeah.
Yeah,
Thank you.
thank you very much, sir. And there's Abdul Halim. I think he told that, as far as I know, my friends are under supervision of Professor Dr. Basu. Thanks again. I mean to say, I think that he might be from IISER Kolkata, that the students are actually working with you. Thank you. Thank you very much, sir. And wishing you all the best. And I hope that you would inspire, and you're already inspiring generations on a very intuitive and a difficult topic like topology. May I ask, sir, what are your future plans? You will be publishing further papers, or you have any further, to travel abroad for any lectures, or you are still with IISER Kolkata?
No, I'm basically like my family is based in Calcutta, so that's
Okay,
one of the primary reasons. So I'll be here, but I do, yeah. So there are occasional conferences that I would have to travel abroad for, or maybe even outside of West Bengal. But beyond that, yeah. So it's here, and I don't know. I would like to maybe with time venture a little bit into teaching, like school students or
right.
appropriate, just to see how it works out. It's more an experiment, but we'll have to see how.
Absolutely. There are a lot of students who contact me also, to know topology, but because of the complex mathematics, I would they really cannot. So I would request you that in future, if you have a plan of writing some books and literature on topology too for the beginners, that would be great. Rajvardhan is writing, I am fortunate enough to talk for you. You were from the first batch of ISI Bangalore. I'm currently in second year in the same course. Thanks for
Yeah,
interaction.
yeah. So
Yeah.
good to
Okay,
know.
sir. Thank you. Thank you very much. Great
Okay.
talking to you.
Yeah.
Thanks
Thank
a
you.
lot. Thank you.
Okay. Yeah. Have a good night.
Yeah, sir. Same to you.